Hello, students. Today we would like to continue looking at the solution of systems of equations, but now instead of just focusing on the linear equations, we will look at systems that have a combination of equations. For instance, when we speak of nonlinear systems, that means one of the equations in the system must be nonlinear, maybe quadratic or logarithmic or something besides the standard linear equations. We've noticed with the Gauss-Jordan method that we have a very efficient and elegant way of solving linear systems. That theory is embedded in the row reduction process, and it can be streamlined and can be computerized. Everything about it is really efficient and easy to execute. With the nonlinear systems, we do have a theory that we've developed in solving equations, but there is no set method. For instance, you basically have to use whatever means you have to coordinate the equations and look for points of intersection. And so what I want to do is share with you several different examples of nonlinear systems. As you continue in the STEM mathematics, you will find great uses for this, especially in the calculus sequence. So for now, let's go ahead and get started. I want to start with kind of the end of the examples that I have because I think it's very interesting. So let me share my screen. I've got another one that's similar to this, but one thing that's nice about it is that it ties in the ideas of the logarithm. So even though this is a very straightforward example, it's a good indication of what I mean by nonlinear equations. So for instance, notice here, we have a system of two equations, but they're logarithmic. And the unknown is the base of the logarithm. So first, that gives us plenty of information about x. We know that x must be a positive real number. And in this particular case, if there is a solution, we're looking for a positive real number other than 1. So what we see here is that the power of x that equals 2y is 3. So we have x cubed equals 2y. And then in the second equation, we have the power of x that equals 4y equals 2. So x squared equals 4y. So these equations are very simple. Had we actually started with these, then you would have said this is a relatively simple system of equations. Now, here you have plenty of leverage, that is, and flexibility. How you choose to actually solve an equation is completely up to you. Do not worry that there is a set method. All you need is a correct method. So now what we notice is that we would like to use a substitution technique, as you've noticed I've written here. Notice if we multiply, in this particular case, the first equation by 2, then we will mimic the 4y that we have in the second equation. So multiplying the first equation by 2 gives us, in this case, 2 times 2y, which is a 4y, and then 2 times x cubed, which gives us 2x cubed. So we'll often find with systems of nonlinear equations that substitution is usually the most valuable. For instance, if we have equations that have the same terms or the same types of terms, we can use the elimination process just like we do with the linear systems. The Gauss-Jordan elimination is predicated on the fact that all of the terms are like. So we can add and subtract, multiply, do whatever we want to do that we do without actually thinking about it. We don't have the same luxury with the nonlinear systems. But now, of course, since we have 2x cubed equals 4y and x squared equals 4y, we can simply set them equal. And now we have a very straightforward algebraic equation. We can simply retire the x squared to the same side as the 2x cubed and factor. Notice here, we'll just extract a 2x squared from each term. So we have the 2x squared times x. Now we've extracted the x squared, but of course we're going to need a 1/2 here to compensate for the 2. And now by the zero product, we see that x squared equals 0, but that just gives us x equals 0. And then of course, if x half is 0, we have x equals 1/2. Now, of course, by the nature of our equations here, we can discard the 0 since a base could never be 0 by definition. So we get rid of that. So the only value of x that we have to consider is 1/2. So now what you can do, you can go back to either of these equations here. Notice I just went back to the least power of x here and divided by 4. So y is equal to 1/4 x squared. Again, you can choose any equation you like. It does not matter. Now at this point, we simply substitute 1/2. So we have 1/4 times 1/2 squared, which is 1/4, and 1/4 times 1/4 is 1/16. So now we have an ordered pair. That is, with 1/2, x equal 1/2, we pair the number 1/16. So we do have a solution, 1/2, 1/16, which you can easily check here to see that that makes sense. For instance, when we have 2y, we just have 1/8. And of course, the power of 1/2 that equals 1/8 is 3. So again, just remember, it's not always important to check every solution. What's most important is to make sure that the solutions you have are sensical. That is, do they make sense in the original set of equations? Not necessarily meaning that you have to substitute and check every piece of arithmetic. But for instance, recall when we worked with rational equations, we had to avoid values of the variable that would render the denominators equal to 0. Of course, that's undefined. But all of the other values that we got in a mathematically correct way, we would say, okay, these are good numbers. They do not produce division by 0. Now, again, you can check anytime. That is always good to do, but it's also good to check that your work is done correctly in the sense that you follow the logic of your mathematics. So you can choose either route. But just again, make sure that what you have is a solution that supports the original system. So this was, I wrote extra here, but this is kind of fun because again, this is back talking about the types of functions that we spent time on. That is the logarithmic function and the exponential. And we see how we can tie those in to a system of nonlinear equations. Now, I've got several examples here from your notes. And what I've done in some cases is I've just drawn a little figure, not Rembrandt, of course, but many times when we think about solutions of systems, especially when you get to Calculus 3 and linear algebra, when you talk about planes, all of the Gauss-Jordan reduction process that we have done will have a nice geometric flavor to it. And so you can add more geometry to that when you have a more thorough discussion of planes that you would get in linear algebra and Calculus 3. But what I've done here is anytime there's an opportunity maybe to draw a sketch of the two equations that are exhibited by the particular equations here, we can see a geometric solution in the sense that we see the actual point of intersection. This is not required, but there are many instances in calculus and in STEM courses where the graph is a very good indication of how you can set up a particular problem. And I'll say more about that as we move through some of these examples. Now, notice in the very first case here, we have a quadratic equation in the first and a quadratic equation in the second. Notice in the second, the square is not completed. We could complete the square. And we would note in the second case, we would also have a circle, as you've noted here by what I have drawn. And I'll say more about that. And then, of course, the first quadratic equation, we're having the standard quadratic equation in x and y, and that clearly is a circle also. So you might be thinking that in this particular example, we could use elimination, but that really would not work because of the linear term in x. So what we can do is just look for a straightforward substitution. Now, notice here, we can look to see what we have in this particular equation here. And if we notice, we've got this x squared and the 3x, and we only have a y squared term. So what I wrote here in blue was simplest, but let me share with you why I wrote that. Notice if we solve for y squared, ladies and gentlemen, we get 9 minus x squared. And so we have one occurrence of y, and that is as y squared in the second equation. So we can use a substitution technique because that will be the simplest. Well, actually our only course of action. So now in the second equation, we have x squared plus 3x plus y squared, which is 9 minus x squared. So we substitute that. So now you can see that the negative x squared and the x squared absorb, and we're left with 3x plus 9 equals 0. Well, that's what could be simpler. Well, we factor the 3, so we have 3 times x plus 3, and by zero product, we just get x equals negative 3. And there is certainly no reason to assume that that would be a answer that would be incompatible with the original set of equations. And now, of course, we're good to go. Notice here, we can just use the boxed equation here to find y. Y squared is simply 9 minus x squared. So if we substitute negative 3, we just simply get a 9 minus a 9, which is 0, and therefore y must be 0. Now you're thinking, well, there's only one point of intersection. Well, when you notice this, and this is an interesting problem, what I did here, and you know how to complete the square, we don't do it very often, but there will certainly be opportunities to do that in your later mathematics courses, and of course in your science and engineering courses, just because it's a technique that's extremely valuable when you're working with mathematics and engineering problems as well as science problems. So notice here, when we complete the square, we need a monic polynomial, which we already have. Notice the square in y is already complete, but we don't have the completed square in x. So we take half of the coefficient of the x term, which is 3/2, and we square it, we get 9 over 4. And now we can write this as a perfect square. This will just be x plus 3/2 quantity squared. So now when you expand this square, you get the 9/4 by squaring the 3/2. And of course, 2 times 3/2 x is 3x, and we get the x squared. So it's probably a good idea just to run back through the completing of the square just to verify that. But now we see that this is indeed a circle with radius 3/2 with center negative 3/2, 0, which I've notated here in red. So what we see here is that the point of intersection between the circles is indeed negative 3, 0. Now, by drawing this, it does open the door to some geometry, especially when you do applications of the definite integral and you learn information about polar coordinates. Because, for instance, we might be interested in the area that would be bounded by the interior of the larger circle, but exterior to the smaller circle, something like this. So when we actually draw this and then we have a visual of what's going on, this can help us to set up the appropriate integrals to solve the problem. So we often find that a sketch of the geometry can be very useful to us. Notice here, I've done the same thing with the problem right here, and let me go through this. So again, the sketch here is optional. It's not required to do the algebra, but there will be instances where you will need a sketch to actually coordinate the process that the problem requests of you. Now let's look at this example here. We have y equals 2x minus 5, and we have x squared plus y squared equals 10. Well, this is an example, like I said at the introduction. This is a linear equation here. This is basically just linear as a two-variable linear equation. If we had 2x minus y minus 5 equals 0, if we put all the variables and constants on one side. And then, of course, we have a circle here, a quadratic. That is the general quadratic, x squared plus y squared equals 10, kind of like we had in the problems in the first example. So now, again, the radius here is clearly between 3 and 4, a little bit closer to 3. And so we look at this and think, well, what I've done here, I've drawn a picture, but that's only using the fact that I figured out the points of intersection. But you could also think of this problem just like you have here. For instance, if you were interested in maybe this area as a calculus problem, it's nice to have a picture just to organize your work. Again, the organization of the work is somewhat benefited by a reasonable sketch that helps you to organize your work. It's not required, but the visual aspect is often very useful when you are doing calculations. Now, notice here, we adopt the same procedure as we did in the first one. Notice here I've got substitution, or it's abbreviated, and we can just see that we can substitute 2x minus 5 for y in the second equation. So now we have x squared plus the quantity 2x minus 5 quantity squared equals 0. And now, ladies and gentlemen, we just have a quadratic equation in x, which we know how to solve. So, with that, let's go ahead and look. We have x squared. And of course, we expand. We have a 4x squared. We have a negative 10x times 2, which is a negative 20x. And then we have 5 squared, which is 25. So now at this point, let's just collect terms. We have a x squared plus a 4x squared, which is a 5x squared. Then we have a negative 20x, and we have, in this case, a 25 equals 10. So now, if you like, just go ahead and retire the 10, subtract the 10 from the 25, and we have what we have here, a useful quadratic equation, but somewhat heavy with the coefficients. So now what you can do is just divide each of the coefficients by 5. We see that that's common to all three, and this will give us an x squared minus a 4x plus a 3. So this is a quadratic equation in x. So we can just write quadratic in x. Notice, and this is going to be something that you'll study in pre-cal when you do the conic sections, but these types of equations symbolize the general quadratic. For instance, let me just go ahead and write that down. We have a x squared plus bxy plus cy squared plus dx plus fy. Well, I'll do an e, might as well keep that in alphabetical order, plus f equals 0. So when we look at this, we have what we call the general quadratic. That is, we have quadratic terms in x and y. We have what we call a mixed term, that is a cross product term, x, y. And then we have linear terms in x and y. And then we have a constant equal to 0. This is what we call the general quadratic. And of course, this can be expanded to 3 variables, as you'll see in Calculus 3, which will define what we call quadric surfaces. When you look at this general equation here, ladies and gentlemen, you have the equation of the conics sections of the double nap cone, and you will study those quite thoroughly in your pre-calculus class, and they will be also used in the calculus sequence, and they're very useful curves. There are applications of the conics that will be with us forever, that were actually studied in ancient times, but then of course with the invention of the analytic geometry and the Cartesian coordinate plane by Descartes, we have an algebraic manifestation of the conic sections that includes this standard equation. So I just wanted to say something about that because I keep referring to it, and I don't want you to think that, well, what is Professor Hollis talking about every time he mentions, a general quadratic? We're referring to this. Now, of course, the completing the squared you know how to do, but this cross product term actually requires trigonometry to eliminate. The completing of the square is something you already know how to do, which translate axes. The translation of axes we understand through function transformations, but the actual rotation is something that requires the sines and cosines, and that will be something that you'll talk about later. Okay, now notice here, we're pretty much done with this. This is an easy factorization. Of course, we have 1 times 3, or 3 we can just write as -1 times a -3. And of course, those two factors add to -4. So we have a very simple factorization. And by the zero product here, we get x equals 1 and x equals 3. Now, of course, at this point, you just simply say, well, I've got these values for x. I can now compute the values for y, and we go back to the original equation here. So when x is 1, we have y equals 2 times 1 minus 5 to give us -3. And then when x equals 3 here, we have y equals 2 times 3 minus 5, which is 1. So we have 1, -3, and we have 3, 1. And notice the sketch here, again, just to provide some geometry. Again, when you study the definite integral and you look at some of the properties, just like you will study tangent lines with the derivative, there will be many problems that can be solved using these new objects. That is the object of the derivative and that of the Riemann integral, which will be very useful to your STEM classes. So again, just remember that often an organizational graph can be very helpful in organizing the particulars of a problem. Now, I just want to continue to do some more examples here. These are not very hard problems, ladies and gentlemen, but we have to just be vigilant. There's no one set way to do any problem. Notice here I have another log problem. Those are just kind of fun. What we find is that we often do the same substitution over and over. I've got some examples of elimination that I'll share with you, but notice when you're dealing with problems in STEM, you often have the mix of different types of equations, and that will actually open the door to approximations method or approximation methods. One method that will be very useful to you will be called Newton's method, which you will study in the calculus sequence. I normally teach that in Calculus 1, and it provides a very good opportunity to get good precision solutions to equations that don't admit to a standard technique. That is, the approximation technique of the calculus is required. And that is one thing that we often notice about calculus. It is a more refined way of doing arithmetic, which we already know how to do. So that'll be something that we'll study later. Now, in this next example, very similar to the last one. Notice we have a linear equation. This is directly from your lecture notes. We have x plus y plus 3 equals 0, again, a linear equation. And then we have a general quadratic. That is, we have x squared plus y squared plus 4y minus x equals -3. Now, of course, you could do the same type of calculation that I did on the last one, but I just wanted to show you an example that's similar to that one, so I'll make sure that the process is very comfortable with you. Notice, just like with the last problem, we can simply isolate the y. But look here, we have, and then there's actually more flexibility here. Notice we have two y terms and we have two x terms. So whatever you do here is completely up to you. You can solve for x or solve for y. That certainly won't cause a problem. And we certainly don't want to introduce unnecessary radicals into a substitution problem. We want to keep the algebra as simple as possible. Now, when we look at this particular substitution, notice here we have y equals -x minus 3, and we can simply substitute that for the y term here. So we have -x minus 3 quantity squared, and then we have the 4y term, so we have 4 times -x minus 3, and then of course we have the x squared term, the minus x, and the -3 from the problem. So notice again, and I kind of mowed over this, when you actually solve for y, you just get a -x minus 3. And then for all the occurrences of y, we simply replace that with that expression. So substitution is simple. So now what we want to do is just clean up the algebra. Notice the negatives here just absorb, so you can just, the squared gets rid of them, so you can pretty much ignore them. We get an x squared. We get a 3x times a 2, which is a 6x. We get a 3 squared, which is 9. And then, of course, here the negatives don't absorb. We get a -4x, and we get a -12. Now, at this point, we just want to collect all the terms. Notice here we have an x squared and an x squared. That gives us a 2x squared. And now we want to collect the x's. Notice here, and lots of things absorb. We have a 6x here, but we have a -4x and a -x. So that's a -5x plus the 6x gives us just an x. And now if we look to see what's left, we have a 9 and a 3, which adds to 12, and we have a -12, which is 0. So we get rid of all of this very handsomely. That is, we just have 2x squared plus x equals 0, and we're like, well, doesn't this look like what we did earlier? So you can factor the 2x here. That leaves behind an x and, of course, a 1/2. So it looks very similar to what we did before, but we don't have logarithms. So now we have by zero product, x equals 0 or x equals -1/2. Again, the same algebraic theorems apply. We don't change any of that. It's like we're back in week 2 doing the same types of algebra. So just remember, with the Gauss-Jordan elimination, we didn't have to introduce new arithmetic. We introduced new techniques for using matrices to solve linear systems. That was new. But we find that the process makes so much sense and it's so much easier than carrying around the variables. Now, with the nonlinear systems, everything is pretty much what we've already done. We don't really learn a new efficient technique. We just practice what we already know how to do and combine that knowledge in a way that gets us to the finish line. So now, if you will, you can simply say, well, what do we need? We've got our boxed equation here, so we can simply use that to solve for y. You can put boxes around things as you work these types of problems just to highlight things that are important. And of course, I probably end up putting too many boxes around things, but again, highlight something that you can use later. Or if you find something that's useful, put a box around it because you probably will have to go back to it. So when x is equal to 0, we simply have y equals -0 minus 3, or -3 clearly. And then, of course, when x equals 1/2, in this particular case, we have the additive inverse of the additive inverse of 1/2. So that gives us 1/2 minus 3. So that's just 1/2 minus 6 over 2, which gives us a -5/2. So now you can see we just pair these up. 0, 3 is our first ordered pair solution. And then, of course, -1/2 and -5/2 is our second ordered pair solution. So very straightforward, very similar to problems we've already done. I think you're going to find, like I said before, the substitution will give you the most powerful technique because it doesn't require that the particular terms be like, okay? Elimination is very powerful, and when we can use it, we will certainly go for that first because it will certainly, well, not certainly, but usually be easier. Now, I just wanted to do another problem that contains logs because it was a little bit different from the last one. So let me go ahead and put the brace here so you see the system. And I got this out of your textbook, again, because it was similar to the other logarithm problem, but had some very interesting adjustments to it. Notice in this case, we have the natural log of x equals 5 times the natural log of y. And then for the second equation, we have the base 2 logarithm of x equals 3 plus 2 times the base 2 logarithm of y. Again, equations in x and y, clearly not linear. Now, how you proceed at this point usually means that you would need to use, as I've written here in blue, the log identities. So by doing that, you can open the door to a substitution that will help you solve the problem. So notice the first thing I want to do here is use the power rule, that is to bring the coefficient here to the power of the argument. And so we have log of x is equal to log of y to the 5th power. Now, of course, the first thing we can get from that is that we have the one-to-one property for logarithms. So we can now equate the arguments of the logarithms because we have the equality of the logarithmic functions. So x equals y to the 5th. So that's the first thing we can get using our knowledge of logarithms. Now, for the second part, what we want to do is use another log identity. So we can first use the power rule to get the base 2 logarithm of y squared, as I've written here, and then transpose this term to the left with the other log term. So this will give us the base 2 logarithm of x minus the base 2 logarithm of y squared, and that equals 3. Now, of course, we want to, again, apply the same properties that we did in the previous problem. So what we want to do is to combine the log terms. The difference of the logs can be written as the log of a quotient. That is one of the identities that mirrors the same property for the exponential functions. Of course, since the base A logarithm and the base A exponential are inverses, we would expect that they would have a one-to-one correspondence between identities. I mean, that's really nice. So now, of course, we just have the base 2 logarithm of x divided by y squared equals 3. Now, at this point, we would like an equation that looks like that. What's a logarithm? Power of the base. The power of 2 that equals x divided by y squared is equal to 3. So 2 to the 3, which is 8, must be the argument. So now we have very powerful results here. So I'll box these and see what they tell us. So now we have, in this case, x equals y to the 5th. And now, of course, if we cross multiply, we have x is equal to 8y squared. So this takes us back to the same technique that we used in the earlier problem. That is, we got the 4 y's, and then we set what those expressions were equal to. equal, and then we moved ahead. So now by just substitution, we have y to the fifth is equal to 8y squared. And of course, we can do the transposition, bring the 8y squared term to the y fifth side. And so now we can factor, in this case, the y squareds. So we have a y squared times a y cubed to give us the y fifth. And then we have a y squared times the -8 to give us the -8y squared, set that equal to 0. So now, of course, we have zero product. So we have y squared equals 0, which is easy. That just gives us y equals 0. And of course, we get rid of that in the case by looking at the original problem. We know that the logarithm arguments must be positive, and 0 is not categorized as a positive number, clearly, when we think about the domain of the logarithm function. So this must be discarded. Now, again, we have a difference of cubes, so that would just be y minus 2 times y squared plus 2y plus 4. Again, our friend, right? Let's write that down. A cubed minus b cubed equals a minus b times a squared plus ab plus b squared. But we know that the second quadratic term has no real zeros. And so we can write it down as I've written here, but pretty much ignore it. It only has imaginary zeros. So the only real zero is the 2. So even if you forgot that, you would not get into any mathematical inconsistency here. So we have y equals 2. So now, of course, we can simply go to an equation of our choice right here and find x by raising 2 to the fifth power, and we get 32. And so now when we pair these two, we have x is 32 and y is 2, and we have a solution to our system. Now, again, just remember, the logarithm functions will necessarily be more restrictive because of their domain restriction. And then, of course, when we're dealing with bases for logarithms or exponentials, that again gives us the restriction of positive real numbers other than 1. So we often have to be a little bit more vigilant about the values that we get for our variables to make sure that they make mathematical sense in the original system of equations. Now, what I wanted to do, and this problem maybe looks a little bit busy, and I'll just say this is what happens when you start overthinking problems, but I wanted to just provide an example of elimination and then also rewrite it in ways. And then I did just kind of this very, you know, not very beautiful sketch, as they say. I don't want to say it's a bad sketch, but it's just a rough sketch of what's going on. If you were thinking about the problem, maybe in terms of a calculus class, using the ideas that we've learned about asymptotes in this problem. But you can ignore this part for now and just look at the top part. Notice what's interesting about this problem that we did not see in the previous ones is that we have terms that are like. You know, we've got terms that can be eliminated using the elementary row operations. We do those all the time with the linear systems. They are the ingredients that allow us to move to the what? In this particular case, the row reduced echelon form. And when we've got that, we have a form that easily gives us the solution to the system. So when we think of elimination, we can always go back to the reduction process, the Gauss-Jordan, and just apply this here, but in a much more simple fashion. We don't write a matrix clearly, and we just think about the elementary row operations. So notice we have a 2 over x squared minus 3 over y squared equals -1. And we have a 6 over x squared minus 7 over y squared equals -2. I just took this out of your textbook because I needed some good examples with elimination. And of course, you could make these up, but that's not necessary either. Notice now, if we would like to look at these, we just have like a 1 over x squared and a 1 over y squared term common to both. And then of course, constants here. So that's not a problem. So what I've done is think, well, let's just go ahead and eliminate the 1 over x squared terms. So you can multiply the first equation by 3. Again, your choice, and nothing is required, just a mathematical effort that gets you closer to the solution. So when we multiply by 3, we get a 6 over x squared. Multiply this term by 3, we get a negative 9 over y squared. And multiply this term by 3, we get a negative 3. Of course, the negative's built in, so not overemphasizing the negative, just kind of tying it into this particular term. So now when you look at this, you're thinking, well, we can subtract these two equations. And what I did was try to do this in a way that gives us nice numbers. So think of just taking this equation and subtracting this one. So 6x squared minus 6x squared is 0. But now we have a negative 7 over y squared. And if we subtract the negative, we get 2 copies. So I just wanted to avoid a bunch of negatives here. You don't have to avoid them. It won't change the answer. And of course, the -2 minus the -3 gives us the 1. So basically, what we have is we've got this added to this, where I've just taken the negative of this. And when you do that, you see that the 1 over x squared terms, supposedly, as we are categorizing them, absorb. So in any order you like, it doesn't matter. So now, of course, it's like, well, another simple equation. None of these systems will give you equations that will be unfamiliar. I mean, at least of the problems that I ask you to do. As you learn more about solving equations and work with different types of functions, then you'll develop some new techniques and identities to use. But what you'll find is that on occasion you may get an equation that requires approximation techniques, and that's where the calculus comes in. So just rest assured at this point that there will be some way to get to a solution using the knowledge that you already have. So now, of course, we just have a difference of 2 squares. So you can just factor this. You can write this as the zero product, if you like, by having y squared minus 2 equals 0. That would be the second step. And then, of course, factorizing the difference of 2 squares, y minus the square root of 2 times y plus the square root of 2. And that clearly gives us the values, in this case, y equal plus or minus root 2. Now, when you have this, and notice the beauty of this problem, we don't have to do the plus and the minus, because of course, when you substitute, the squares absorb the minus. So you get 2 for the price of 1. So you don't have to do extra work. So now, of course, when y is equal to the square root of 2, we can just use the first equation. So now, of course, the square root of 2 squared just gives us 3/2. Notice I've added this term to the right-hand side. So we have 3/2 minus 1, which is a 1/2. And then we have 2 over x squared. So just reciprocate if you like. So we have x squared over 2 equals 2, cross multiply, and we just get x squared equals 4. So at this point, as I'm saying before, when you reciprocate, you get x squared over 2 equals 2. That's the reciprocation here. And then when you cross multiply, you get exactly this. And now, of course, that just gives x plus or minus 2, just like we had here without putting in all the extra steps, just using the square root property. So now you're good to go. So we can pair the square root of 2 with plus or minus 2. here, and here. And then, of course, we can pair the negative square root of 2 with plus or minus 2. That's it. So you get the 4 solutions without having to do that many substitutions because of the squared nature of these terms. Now what these are not, you think of the asymptotic effect when you have 1 over x or something like that, and you're like, well, how do I do this in a way that's going to make any sense? So what I tried to do was look at these solutions now and notice how they're symmetrically arranged. For instance, these are just symmetric through what? The x-axis, the y-axis, and the origin. Okay, it's like we're working on a circle. When you think about this, you could just draw the circle here that contains these points. But the beauty of this symmetry can be seen again just by working with these equations. But if you wanted to, and I won't go through this very thoroughly, what I wanted to show you here is that you can take the equations and then just solve for y squared in both cases, as I've done here. This is just very simple algebra, getting a common denominator. I just wrote observe here and just started sketching things out because I often do this when I'm working problems in calculus. But all this is college algebra. And the students are like, well, what are you doing? I say, well, this is college algebra. So we don't have to apply any fancy constructions from the calculus. We just apply our basic understanding of algebra. But notice here, we have the y squared equals 3x squared over x squared plus 2. Again, if you look at that as a rational function, you're good to go. The degree upstairs and downstairs is the same. But if you apply the square root principle, you get y is plus or minus the square root of this. So now as x passes to infinity, you just get basically the square root of 3 as an asymptote. So it's really interesting when you look at this and you think about what's going on. Now, one thing that I noticed here, let me get rid of that 2 there. I don't need that. I've just got the square root of 3. A little bit extra there. Don't need all that. So there we go. And notice when you do this for the second equation, very similar technique. Just, you can take a screenshot of this and just verify this. Very simple algebra. Now notice we get the 7x squared over 2x squared. When you do the ratio, degree upstairs and downstairs are both 2, then you got the square root of 7/2. So again, 7/2, when you do the division, that's 3 1/2, okay? So that's going to be a little bit bigger, but not a whole lot. So I've got the square root of 7/2 here. So now when you actually do this, you basically have horizontal asymptotes. That is, this x passes to plus or minus infinity. So you can think of, in both of these cases, as the curves having a symmetry that is reflected in both of these cases. That is, when you look at this radical here, it's defined for all real numbers. There, you don't throw anything out. Of course, you're seeing the origin is kind of kicked out here, so I really shouldn't be passing through the origin here. But you look at these, the squares here, they're defined for all real numbers. And so when you think about the positives and the negatives, they cover the entire real line. So when you look at this first function here, you've got a piece that goes here and you've got a piece that goes here. And then when you look at this particular, and then of course, if you take the negative of it, you've got the reflection in the what? In the x-axis. And of course here I've erased this so much. There we go. That kind of goes that way. Like I said, it's not Rembrandt that approaches that right there. And then, of course, when you take the negatives, you're just reflecting in the x-axis. So you get all of these beautiful curves that cover the entire real line. of course, kicking out the origin. And so then what I've done is I've just dotted in the intersection of the curves, because what's going to happen is that as the curve tends here to the, and I'll write this in, y equals the negative root 3. And then here we have y equals the negative 7/2 as we get from this curve. So the beauty of drawing a picture, for instance, you might be in a calculus class and you have to graph this and show increasing, decreasing, and concavity and things like that. But you're thinking, wow, these are just curves that we found their solutions using college algebra. And then if you manipulate the algebra, you can see what the curves actually look like. And notice I haven't used any fancy calculations here. I'm just using the properties that we have about symmetry and the properties about limits at infinity when we think about horizontal asymptotes. So the idea here is that you can think of this geometrically. Again, this is just a little extra. A lot of times when I teach mathematics, I always think about where my students have to go. So take the time just to look at this and to solve for y squared and to create the two functions that you get out of this. You get a curve that's above the x-axis and one that's below in both cases. And then when you look at the intersections, you get all of these. So buried in this are all of these curves here, these 4 different curves. And it's amazing. It's amazing how simple it is if you think about this problem as a system of nonlinear equations. So again, a very elegant problem in college algebra. Now, the last example, or the last two, actually, I've tied this into one. I got a little bit busy with this, but maybe not as complicated. Not the last problem wasn't complicated, but here the pictures are a little bit easier to see. Notice when you have the 1 over x squared and you're adding these and you're moving things around, the complication comes up. But again, just notice these aren't standard curves. These just remind you of rational expressions. And if you had to graph it, you'd have no, this is why we have no vertical asymptotes here. And this is why this is such a nice problem. Again, no vertical asymptotes because the denominator is never 0. And so you get these beautiful symmetric curves. Now, let's look at another case of elimination. The substitution's fairly straightforward. The elimination, again, reminds us of the Gauss-Jordan process. And what I wanted to show you here, when you get to the general quadratic, notice when the coefficients here vary, we don't have the symmetry in the coefficients of the x squared and y squared terms. So this becomes an ellipse if it is an if it's a curve at all. I mean, we don't make the assumption, we say, okay, this has this form. If a curve exists, it would be a circle, or it would be an ellipse, or a hyperbola, or a parabola. So again, we have to investigate a little bit further. Now, notice here we have another general type quadratic equation, but we have a negative here. And when you study the conic sections, this will actually be a hyperbola. If you've ever been by a nuclear power plant, you see these large hyperbolic towers. They're called the cooling towers. And the geometry of the hyperbola or hyperboloid of one sheet, that is, it has this shape that is very easily recognized. The cooling properties that you get from that particular geometry is amazing. There are reflective properties that exist for all of the conic sections that have been known to the ancients. And of course, we know how to prove them analytically with the refinements that we made to our mathematics, but the ancients figured them out just by their genius and applying them to having a better way of life, at least in ancient times. So again, the the general quadratic opens the door to the quadric surfaces that you will see later, and they will be of great interest to you. So now notice here, this is not as complicated as the last problem, because in the last problem we had 1 over x squared, 1 over y squared. Here we just have the standard. So now you can look at this and say, well, we can multiply, in this particular case, the first equation by 2 because we have a negative here. So when we multiply the first equation by 2, we get an 8x squared, a 6y squared, and an 8. And then, of course, as I've written here, we can absorb the y squared terms simply by adding. So this is, again, an elementary row operation. So this gives us 10x squared equals 5. And now, of course, the 5 and the 10 absorb by 2. So that gives us x squared equals 1/2. So x, by virtue of the square root property, is plus or minus 1 over root 2. Now, just like we did before, we don't have to beat ourselves up. We can just go ahead and solve for the y squared using a very simple equation that we have from the very beginning. So 3y squared is equal to 4 minus 4x squared. So now what we can do is just go ahead and factor. We've got 4 times a 1, in this case, minus a 1/2. Now notice here, and this is kind of interesting here. When you substitute the 1 over root 2, that just gives you a 1/2 when you square it. And notice what I did. I just factored the 4 here. So that gives us the 1 minus the 1/2. So I don't want you to think I just pulled the wool over your eyes. In this case, when we substitute here, the square is removed and we just get a 1/2. So now we just have 4 times 1/2, which is 2. Okay. So now at this particular case, 3y squared equals 2. So y squared is equal to 2/3. And therefore y is equal to plus or minus the square root of 2/3. So again, we get 2 for the price of 1. All the terms are squared, so we don't have to do all of that algebra. So notice we just pair everything off. With the 1 over root 2, we can pair that with the plus and minus square root of 2/3, which I've done here. And then for the negative 1 over root 2, we can again pair that with the plus or minus square root of 2/3, which we have here. Okay, so again, you don't have to work very hard if every term is squared. You've got the square root principle, and so you don't have to substitute the minus of a particular value that you have because it will simply absorb. Just thinking about even functions, okay? So at this point, here's where the algebra stops. That's your solution. You're done with this problem. But I did want to make a couple of comments here. When you do your conic sections, you will simply think of the ellipse like you think of a circle, but what you're wanting to do is you're wanting to write a standard form for the ellipse. You may have seen some of this in high school, so this may not be completely new, but we have something like x squared over a squared plus y squared over b squared equals 1. And what we're noticing in this particular case is the 2 divided by the root 3 is bigger than 1. So this is the axis, the vertical axis that contains the foci. So that's what you'll study when you do the conic sections, and the particulars are about the ellipse. So when you draw the ellipse, it is longer in the vertical direction, as I've notated here, just very simply, very, very rough sketch, nothing overly precise. Now, notice again, in the second equation, if we divide by -3, the squared terms flip. So we basically get, in this particular case, we get a -6y squared divided by -3, which gives us y squared over 1/2 if we just move everything downstairs. That is, you write 6 as 1 over 1 over 6, and then 3 over 6 is 1/2. And then, of course, we do the same thing here. We write 2 as 1 divided by 1/2. So now we get a 3/2, 3 divided by 2 in the denominator, and the minus sign here. So now we're seeing that the intercepts are on the y-axis as opposed to the x-axis. This defines a hyperbola. Now notice I haven't gone ahead and done the same thing that I've done here. I've just left these squared. So this would just be 1 over root 2, and this would just be the square root of 3/2 if I wrote it like I did here. Now, what I wanted to show you is that even though this is a very rough sketch that we have here, that I wanted to show you that we're going to have a simple ellipse intersected by a hyperbola. And so what we notice here is that we can use the fact that we've solved for these points simply to draw this sketch without a whole lot of extra work. Notice here, I have a formula for the slant asymptotes that is y is equal to plus or minus 1 over root 2x. And basically what we do is we get that by taking ratios here. And what happens is that the root 2's absorb and we're just left with the 1 over root 3. But again, that's some extra calculation that you'll do when you take pre-calculus. But notice the picture of these points of intersection are simply the intersection points between the ellipse and the hyperbola. Hyperbolas and ellipses have a very recognizable curve sketch. And so if you're just simply trying to show in a geometric way the points of intersection, you can do this. And now again, you see you've got this beautiful symmetry. You have this y-axis symmetry. You have the origin symmetry. You have the x-axis symmetry. So all that beautiful symmetry there is the benefit of having all of these conic sections centered at the origin. So again, this is extra, just like it was on the last problem. But I don't want you to think that we just do mathematics, ladies and gentlemen, in a vacuum. The idea is that if you have some idea about what's going on here, when you see this again in pre-calculus, there will be some understanding of where all of these ideas are coming from. What you'll do in pre-cal is that you will formally define the conic section, and then you'll understand why these particular forms exist like they do for the standard Euclidean circle. So that will be something that will be of great interest to you. So what I've tried to do is take advantage of the fact that when we work with these nonlinear systems, we have some really interesting intersections of conic sections that again will be very, very useful in the calculus. Now, again, I just want to emphasize that when you're dealing with the Gauss-Jordan elimination for the row reduction process to solve linear systems, you have plenty of flexibility. You can combine equations to avoid unnecessary fractions. You get your reduced row echelon form and have a very simple way to state the equation solution or the system solution. With the nonlinear systems, you are basically in control also, but you do not have so much of an algorithm to solve. As we've noticed in the problems we've done, there's been plenty of flexibility as to how we can approach them. So don't think that, well, am I not doing this the right way, or do I need to do this a certain way? As long as you are combining the equations and applying good mathematics, the solution will be computed correctly. So just remember, with the linear systems, you have lots of structure. With the nonlinear systems, you have structure, but you have more flexibility. And don't worry that again, you may solve the system differently from a friend or a colleague, and both of you get the same response. The idea is that the correct mathematics will supply a good solution. And as you have time, think about some of the geometric constructs that I've talked about, and think about how you can rewrite a particular equation and see some of the ideas that you saw in earlier types of problems to make connections. Again, remember, as you move into physics, as you move into the calculus sequence, pre-calculus, other science classes, engineering especially, nonlinear systems will come up quite often. And so what we try to do is make an introduction to that so you can start thinking about how you can apply the algebra that you know to solve these systems. And again, remember, every problem will introduce new challenges, but that's okay. As you do a new problem, you develop new techniques. So I hope this has been interesting. Just remember, as you move into the pre-calculus course, you will continue to do intensive type algebra, but you will also learn about the conic sections. You'll learn about sequences and series, and you'll learn about trigonometry, which will be extremely beneficial for the calculus sequence. Well, that's all I have to say about this. We'll see you later.